In this video, we're going to explore the synthesis of alkynes from alkenes. Why is synthesis in quotes, you ask? Well, this is not really a synthesis to make this molecule from this alkene because we didn't make any carbon-carbon bonds. It's a transformation. Before we begin, though, we have to review an old reaction and look a little bit ahead at a new reaction. The old reaction is the halogenation of an alkene using a halogen such as chlorine, and we get a vicinal dihalide with anti-stereoselectivity. This works for any alkene with carbons or hydrogens on the end. And looking ahead at 9.3, we see that if we do have a halogen in a molecule, we can make it undergo what's called a bimolecular elimination, short form E2. What happens is a halogenated hydrocarbon in the presence of a strong base and heat being required for a reaction that makes a less stable pi bond from a molecule that did not have any pi bonds at all, sigma only here. The combination of a carbon with a halogen, a strong base, and heat will give a new alkene. In our video on 9.3, you would see that the alpha carbon is the carbon with a leaving group, the halogen here. Beta, one away from alpha. The beta carbon must have an H. The base grabs the H, and you make a pi bond. Combining these two processes, we see that we could halogenate our alkene in the question right here with chlorine, creating this species here. And if you look carefully at this reaction here, if you have two halogens, you can make two pi bonds. So we're going to follow that up with the bimolecular elimination number 1, calling this the alpha carbon with a halogen. Beta carbon loses an H to the NH2 minus, and you make a pi bond in between. And realizing you still have a halogen, you can reverse the Greek lettering. And what happens with the second mole of NH2 minus is you do the same chemistry, grabbing this H, making a pi between alpha and beta, and chlorine leaving. You have your alkyne. So you think you're done. You think you've accomplished your mission of making this molecule up here. You have not. When you added an excess of a NH2 minus to make this, which you had to use at least 2 moles, you also created a terminal alkyne with a pKa of 25. NH2 minus will do this very quickly. Acid-base deprotonation, and you'll make NH3. Truth be told, this is the 3rd mole of NH3 you've made. You made one here, and you also made one here. Well, didn't accomplish your mission, but you're only one acid-base reaction away from doing so. I need an acid with a pKa less than 25 because I'm going to add an acid to this and create a new acid with a pKa of 25, and we all know that pKa reactions always go from lowest pKa to highest pKa. Acid, cheap, pKa less than 25. Water comes to mind, pKa 16. So, step 3, we'll create our terminal alkyne. We've finally accomplished our mission of box A. Chlorination, followed by excess strong base and heat, followed by water to create our terminal alkyne. The first 2 steps of this are repeated throughout each box, so let's reveal those. So, we have made using steps 1, 2, and 3, we made this. Steps 1 and 2, though, made this. So step 3, to make a deuteral version of a terminal alkyne, you would not use H2O as your acid. You do something with an identical pKa, but providing a deuterium. That would be D2O. So step 3 there gives our requisite terminal deuteroalkyne. Sequence C does do some synthesis. We need a new carbon-carbon bond right here to a methyl group. That is our classic nucleophile here from steps 1 and 2 reacting with a carbon that has a leaving group. There's a video on that. And methyl bromide would give us the extra 1 carbon. So now I have made this key molecule, which can be converted to either a trans-alkene or a cis-alkene. There's the key molecule. How do I convert that to a trans-alkene? Well, first, I got to put the methyl on there like I did before, and that's true for both of these. And then how do you convert the internal alkyne here, created in steps 1, 2, and 3, to a trans-alkene, and that is sodium and ammonia dissolving metal reduction in chapter 7 as well. And now the final question is, how do I convert an internal alkyne down here to a cis-alkene? And that involves either hydrogenation using Lindlar's catalyst or borane followed by with acetic acid. Hydroboration protonolysis, we call that. And that gives a cis-alkene. So there you have it. This is how you can make alkynes from alkenes and do some chemistry that we know that alkynes can do. I hope this video has been useful for you to understand this, and I look forward to our next video.